Hi, in this video, we'll be creating GPT from the ground up. In order to do that, we'll be constructing this architecture right here. Now, this architecture has a lot of parts, but by the end of this video, you will be able to have a complete understanding and intuition about how to code up each and every part. Before we do that, we need to understand the intuition behind how actually a GPT trains and what kind of data set do we need to construct in order to train the GPT. So let's look at this sentence. The cat sat on the mat. Here we will teach the model to predict the next word in the sentence based on the basis of all the previous words. Now you might have a question. Why are we taking all the words instead of just one previous word? So the reason behind that is that the language is deeply contextual and the meaning of the current words depends on all the previous words. Therefore, this is how we would go about training the model. So before we begin constructing our dataset, we need to make sure that our words are represented by numbers. And for that reason, we do tokenization. So I have gone in depth about tokenization in another one of my videos, but we'll keep things simple here and just assign a unique index to every word. So what we do here is pretty simple. We construct a vocabulary using our sentence which has all our unique words, and we assign an index to each of our words. Then we can use this vocabulary to encode back our sentence. But we face another problem, and the problem is that words are inherently complex and one word can mean a lot of things, and for that reason it becomes really inefficient to represent our words with just a number. So we use something called embeddings for each of the words. We basically represent each word with a vector of n dimensions instead of a number. Let's take a look at what happens. In this image, I have a bunch of food items plotted in 3 dimensions. And my dimensions are desertness, sandwichness, and liquidness. Now, if I try to classify apple strudel, I would say it ranks high on the dimension of desertness and sandwichness, but it's not so much of a liquid. And I can do this similarly for all the other food items present in this embedding space. So I need a similar concept. I need my model to learn a similar representation of the text I'm giving. If we talk about GPT-2, GPT-2 had about 12,000 dimensions for every word present in it. And that's a lot of dimensions. So let's visualize how an embedding space of this sort would look like when our model learns it. Okay, so this is an embedding space represented by trained by word2vec, and as you can see here, these are a lot of vectors. If I click on any one word, suppose I click on hills, then I'll get all the words that are related to this word hills, and I want my model to learn something similar, that you can plot all the words in this representation space, and if you treat each word as a vector, it learns the semantic similarity between every vector present in that embedding space. If we want to represent our tokens using embeddings, then we'll have to create a lookup table where we store an embedding for every token present. So suppose we have a vocabulary of 5, so you'll have tokens from 0 to 4, and we can use this lookup table as a dictionary in order to fetch the embedding of the tokens. So now our input shape will be number of tokens by dimensions. So if I have 6 tokens and 3 dimensions, so my input shape becomes 6 cross 3, and if I increase my number of dimensions to 256, then my input shape will become 6 cross 256. Let's see how to handle data in batches. So if we have a batch size of 2, it means that we have 2 sentences, and let's assume that both the sentences have 6 tokens each. So my dimensions would look something like batch size into number of tokens into dimensions. Now why is that? Because if you remember, number of tokens by dimensions is my one sentence, and this is like I'm stacking multiple sentences on top of each other. So if my batch is of size 2, I'm stacking 2 sentences on top of each other. So my dimensions become B cross T cross C. Let's take a look at a small scenario. If I give you 8 sentences and each sentence has 6 tokens and each token has an embedding dimension of 3, how would the dimensions look like? Try to pause the video and think about it. Well, if I give you 8 sentences of 6 tokens, then my dimensions would be 8 cross 6 cross 3, because I have 8 sentences of 6 cross 3 stacked on top of each other. Let's talk about the final augmentation we are required to do before constructing the dataset. Now, remember the example in the start of the video. In order to represent that in matrix form, we need to shift our target values to the left by one position. Now, why is that? It is because if I have a sentence in the heart of the city, and what I need to do is I need to predict that if I give you an input of in, I want my model to predict the, and if I give you in the, I want my model to predict heart, and so on. So if my targets are shifted by left, then naturally I get the example that I showed in the start of the video. So this is something that our inputs and targets should look like. If I have 4 tokens of 256 dimensions and 8 batches, then my targets should all be shifted by left with the same dimensions. So this brings us to task number 1. Your task number 1 is that you need to create a dataset class, and you can read about dataset and data loaders in PyTorch documentation. So the parameters that you'll be given will be the text, which is the input text, the tokenizer. You can use any tokenizer of your choice. You can either encode it using the vocabulary, or you can use something like tick token. Max length, which is the maximum context length of the sentence, suppose 4 tokens or 6 tokens or whatever. And stride is the length by which you're shifting the input in order to construct the targets. Then you need to use the data loader to load the dataset into batches of a particular batch size. So this is the code in order to do that. Let's go through it step by step. So first I have this text file called the verdict.txt. I am reading it in my raw text variable, and I am using the GPT-2 encoder. Then in my dataset class, what I am essentially doing is I am initializing my input and target IDs, and I am encoding the text and storing it into token IDs. Then my input chunk consists of my current index to my max length, and the target chunk is just shifted by 1. I append both of those in my inputs and targets, and my length would return the length of the input IDs. The get item function would return the item that I want. So let's talk about the data loader function. This is basically loading our data into batches of a defined batch size. So here I am initializing my data loader with a batch size of 2, maximum length of 4, and stride of 4. So if I try to access my data loader, I'll get my first batch and second batch. So you can see here my batch size is 2, maximum length is 4, and stride is also 4. And these are basically my inputs, and these are my targets, and you can see that my targets are shifted by 1 with respect to the inputs. So the next task is to add an embedding dimension to the inputs you got from the data loader. So the input you got from the data loader was batch size by number of tokens, and what you need to do is create a lookup table and take the embeddings from there and convert this into something like 8 cross 6 cross 256, where 256 could be the output dimension. You can take any number here. This should be a variable. So here is the code for task 2. I have my output dimension specified as 256, and I have the vocabulary size of the tokenizer, which is around 50,000. I will initialize a torch.nn.embedding layer, which would be my vocab size by output dimensions, because as you saw in the lookup table, I should have all the tokens listed here and all of my dimensions here, so I can access them like a dictionary. So you can see in the code that I have a token embedding layer. Now all I need to do is I need to fetch my data, or like my inputs and targets, from my data loader, and I need to pass my inputs to the token embedding layer. What this does is that it gives an embedding to each and every token by treating this as a lookup table. So my final shape becomes 8 cross 4 cross 256, which means that I have 4 tokens, each of 256 dimensions, and I have a batch size of 8. One final concept in our dataset preparation is the concept of positional embeddings. So take a look at these two sentences. The cat sat on the mat, and the mat sat on the cat. If we encode these two sentences using token embeddings, then we'll have the same meaning, because the embeddings for each of the individual words are the same, which is not something we want, because we can see that these two sentences are different. So we need a way to encode positions as well, and for that purpose we use position embedding. So if I have 6 words in the sentence, I can assign a word to every position. P1 to P6, I can have an embedding of 256 for each of the positions. And as I already have an embedding, a token embedding for each of the words, I can add them, and this will give me a unique embedding which will be the combination of the particular token and the position of that token in that sentence. So if I add these two, I will get different meanings for these two sentences now. So here is the code for positional embeddings. We initialize another torch embedding layer with context length, output dim as the shape, and what we do is that we just add it to our token embeddings, and that gives us the final input embeddings. Now this is what we are going to feed to our GPT model, because this has the encoded information of the tokens itself, but also the positions, and we also created our targets. So our dataset creation part is done. It is time for some attention mechanism. This is the heart of the GPT model. Now let me ask you a question. Whenever you read a sentence, do you pay attention to all the words? No, right? You selectively pay attention to a few words. And this is what the attention mechanism is trying to do. In this sentence, if I focus on the word money, I would know that it is related to the bank in which it was kept. Or I can also say that this was the money that was stolen by the bank robber. This is known as self-attention, where one word pays attention to some of the words in the sentence selectively and tries to ask questions from the rest of the words to see if some of the words are significant to the current word that we are trying to focus on. So how do we make the words pay attention to each other? We represent every word with a key query value pair. Key is what each word represents, query is what each word asks, and value is what each word means. In this sentence, if I pick money, my query could be, where is the money kept? So if I represent this query by Q10, I could be comparing my query with each and every one of the key. And I can compare that using the cosine similarity between two vectors. So if my cosine similarity between Q10 and K7 is high, that means that my query that the money is asking is highly related to the key of the word bank. So this is the idea behind key query pairs and calculating and computing the cosine similarity using the query and the key. So my weight matrix would look something like this. I'll have queries on the left and keys on the top, and my values will be the similarity between the key query pair. Okay, so what do we do with these similarity score and this weight matrix? Well, we can treat this similarity score as the weights for each of the words, and the value vector represents the actual value for each of the words. If we take a weighted average of this, we'll get the context vector of the word money. Now why is that? Because if you see the query that money is asking, we are comparing that query to the key of every word and getting a similarity, which are the weights. These weights represent how much weight do you want to give to a particular value of every word. So if you take the weighted average of all the values, you'll get how much actual context is money giving to the whole sentence. And that context is what is important to us, and it is exactly what we need to feed to our model. So we can now use the weight matrix to calculate the context for each and every word, and we'll get a context vector for every word present in the sentence. Now the question is, how do you make attention trainable? Because currently we are just computing similarity between vectors, but the model is not actually learning anything because the key query value pairs are already given. So how do you make the model learn key query and value of every word? So we need to initialize a weight matrix WK. What this will do is that it will convert our output embedding to an embedding of some other size, and this can become our key. So our 8x256 input shape can become 8x64, and our model will essentially be learning this matrix WK. We can similarly do this for our query and values, and we'll get our key query values, all of them of the same shape, and then we can use this further into our model. So let's look at a vectorized form of attention. This is the formula, which is the softmax of q into keys transpose divided by the square root of the dimensions of key into value. Now this formula looks complex. Let's see how this works through diagrams. So if I have a query So I have 4 tokens and each token is of 64 dimensions. So I have 4 tokens, 4 queries, each query of 64 dimensions, and I will multiply it with the transpose of my key vector. So what this multiplication would give is something similar to what we have seen before. So you're taking the dot product of query 1 key 1, of query 1 key 2, of query 1 key 3, and of query 1 key 4. This represents the weights of query 1 with respect to the whole sentence. So this is your weight matrix. So this is query 1, query 2, query 3, query 4. And when you multiply this weight matrix with the value vector, what you get is the formula for the weighted average of the context vector. So here k1 q1, k2 q1, k3 q1 and k4 q1 are the weights, and you're multiplying these weights with their respective value, as you can see here, and this gives us the context vector z1. If we see how the dimensions work, this is giving us a 4x4 matrix because we have 4 words in the sentence, and multiplying this by value again is giving us a 4x64 context vector, which is the same size, which is the same shape as the query vector. So this makes sense. And yeah, if you want to implement this, this is the formula, which obviously brings us to our task number 3, which is you need to make a self attention class v1, and the parameters that will be given to you will be the input embedding dimensions, the output embedding dimensions, and obviously the input text, and you need to return the context vector. You can take the input as 8 by 256, and let's see if you can implement a self attention class that computes the context vector like this. So here is the code for the self attention mechanism. In my class, in my init function, I am specifying the input and the output dimensions, the key, query and value matrices that will be trainable. So it is converting my input dimensions to output dimensions. So in my forward function, I'll get my keys if I pass my input to my w key, input to w query and input to w value. So I'll get key, queries and values from here. Then I'll apply the formula, which is queries into key transpose. I'll take a softmax, I'll normalize it here, and I'll get the context vector by multiplying my weights with the values, and here I'm returning the context vector. So if my input embedding is 256, output is 64, and number of tokens is 8, and if I pass my input into the attention class, I'll get something like this, and the shape is 8x64. So let's talk about casual attention, right? We have looked into self attention, but the problem is that self attention was kind of cheating, because while training a GPT model, you're not allowed to look at words that you haven't predicted yet. So if I have a sentence, your journey starts with 1 step, you are not allowed to look at the future words when you're giving the input. So that's why we have to mask out the future words. So for that, we apply a casual attention mask, which is just masking out the upper triangular matrix. After that, you apply a dropout in order to reduce overfitting, because this is going to be a very large model, and your final weight matrix would look something like this. Then you use this weight matrix in order to compute the further calculations that we did here. So this brings us to task number 4, which is that you need to make a casual attention class v1, which takes in parameters of input embedding dimensions, output embedding, the input text, and the dropout parameter, and it should return a context vector. One thing that you should keep in mind is that it should be able to handle batched input. So if I give you a batch size of 2 and the dimension is 2x8x256, it should be able to handle these batches of data and return with the correct context vector in terms of the output dimension. So here is the code for the casual attention class. I'm specifying all of the parameters in my init function. Here I have made a mask in order to mask out the future words. So this will be an upper triangular matrix, and I'll leave my diagonals to be 1. So I'll exclude the diagonal here, and all I need to do extra is I need to mask out my weight. So I'll replace all my weights with torch.infinity with negative infinity so that it discards it. Here I'm just returning the context vector. One change that I've made is that I'm doing that I'm taking the transpose along the first and second index of the keys because it needs to be able to handle batched input. So if I look at the dimensions here, if I have my input as 2 cross 6 cross 256, then my output is 2 cross 6 cross 64, which should be the correct output. Alright, so this is the final boss of attention, also known as multi-headed attention. But it is actually very simple. So if we take the same sentence, we were focusing on this word money, and earlier it was only asking one query. Now what if one query it can ask several queries? So that is essentially the idea behind multi-headed attention, that instead of just one query value and key pair, you have multiple heads of query value and key pairs. So if my number of heads is 8, I have 8 query value and key pairs, and that's it. So the only tricky part here is figuring out the dimensions. Now the casual attention class that you have implemented, if you execute it sequentially and stack all the context vectors, then you can get something similar to this, but we won't do that. We will do something much more elegant, and we will play with dimensions in order to figure out multi-headed attention. So suppose my input matrix is 2 cross 4 cross 128, and I multiply it with my key vector. So I'll get my keys, which is 2 cross 4 cross 256. Now assume I have 8 heads. So I'll divide 256 by 8 and I'll get 32, which would give me 2 cross 4 cross 8 cross 32. Now I'll take a transpose between these two values. So this becomes 2 cross 8 cross 4 cross 32. Now why did we do this? As you can notice, this thing denotes that we have 8 heads and each head is of 32 dimensions. So, and 2 is the batch size. What we did is we converted our 256 dimension into 8 heads, each head of 32 dimensions, and we took a transpose. Now what we can do is we can carry out normal operations using this dimension. So we'll apply our normal formula. We multiply queries with keys transpose. We'll get 2 cross 8 cross 4 cross 4. Here is the same deal. 4 cross 4 is the weight, and as we have 8 heads, we have 8 4 cross 4 weight matrices. So we apply masking plus dropout to the weights, and when we multiply it with the value, we'll get our context vector. Before that, you need to remember to take the transpose because we took transpose initially, and when you convert it to the final form, it becomes 2 cross 4 cross 256, which is essentially the same dimension as our keys, which makes sense because they all need to be of this same shape. So this is essentially how you would carry out multi-headed attention in matrix form. Obviously now I think you can do task number 5, which is that you need to make a multi-headed attention class. The parameters will be the input embedding dimensions, output embedding dimensions, the text, the dropout parameter, and the number of heads. This should return the context vector. Now we have come to the final level, which is piecing together the GPT model. Before we piece everything together, we need to understand the intuition behind training a GPT. So I have a sentence here. I tried to catch some fog, I missed. We convert this sentence into its positional plus token embeddings. So I'll get my embeddings from here. And then we apply self-attention and return our context vector. We will pass each of these words to a feed-forward neural network so that we are able to have a non-linear representation for each of the words, because everything that we did up till this point was a linear multiplication. So we need some activation functions and some non-linearity so that our model learns to adapt well. And then what we can do is we can multiply this output and convert it into a one-hot encoded vector of our vocabulary size. So if we had 6 tokens and our vocabulary size was around 50,000, then our matrix would be 6 by 50,000, and we can use that to compare to our target and use some form of loss like cross entropy loss and compute the loss of our actual sentence and the predicted sentence. These are the parameters of the architecture we're trying to build. So this the GPT to 124 million had a vocabulary size of 50,000, context length of 1024. This was the embedding dimension. Multi-attention heads were 12. Number of transformer layers are also 12. The dropout rate was 0.1. So we are going to be using these parameters. Okay, so let us quickly see the implementation of the remaining blocks of our GPT model. So layer normalization essentially normalizes your inputs. This helps in better gradient flow among other things. And we also have scale and shift, which are learnable parameters. So the model learns these as well in order to optimize the gradients in the best way possible. Then let's look at the GeLU activation function. Now the GeLU is used over ReLU because ReLU is not differentiable at 0, but GeLU is differentiable at 0, so this makes it better than ReLU. This is the code for the GeLU activation function. So let's take a look at the feed-forward neural network. We will have two layers. We'll have our input. We'll scale it to 4 into embedding dimension, and then we will scale it back down to embedding dimensions. This is what the code would look like. Obviously, we would have the GeLU activation function in the middle. So these are the two linear layers that we are going to use. We also have shortcut connections so that we don't have the problem of vanishing gradients, and we allow the gradients to skip connections and flow over to the next output. So we will also be implementing that. Now we have all the components ready to build our transformer block. So the task 6 is that you need to create this decoder block, not this whole thing, just this decoder block. So layer norm, mass self-attention we have already implemented, then the skip connection, layer norm, and the feed forward neural network. So this is the code for creating the transformer block. So it's very simple. So the attention class that we made will put all of our params from our config dictionary here in self.attention. Then our self.feedforward is going to be the feedforward neural network that we created. We'll have two layer norms, and then we will also have a dropout. So in our forward connection, we will be passing it to the first layer norm. Then we'll be getting the output of attention. Then we'll add a shortcut connection. After that, we'll do another layer norm, feed forward, dropout, shortcut, and we'll return X at the end, which, if you can see, resembles this exact architecture. What you have coded just now is called a transformer block, a decoder only transformer, and we'll be stacking these on top of each other in order to create our GPT. So I think you know what the next task is going to be. Obviously the next task is create GPT. Now it should not be this hard, because all you need to do is, in order to create a GPT, is stack 12 transformer decoder layers on top of each other, and finally feed their output to the final layer norm, and you convert it into a one hot encoded vector over all the tokens in your dictionary, and that's it. Then we'll have the GPT model created. So tokenized text, embedding, positional embedding, dropout, 12 decoder blocks, final layer norm, and the final linear output layer. So if you're ready, let's see the code for this. This is the code for our GPT model. Yes, it is this short because we have coded up most of it. So we have our token embeddings, positional embeddings, dropout. Then we will have our transformer blocks, which is going to be the sequence of our number of layers. We'll have our final layer norm, and our output head will have the shape embedding dimensions by vocab size, because we need something to iterate over the probabilities over the size of the whole vocabulary. So our feed forward would look something like this. You feed in the input, and then you convert it into token embeddings. Then you convert it into positional embeddings. You add the token and positional embeddings. Then you do dropout, you pass them, you pass the input through all the transformer blocks, the final normalization layer, and when you multiply the output head with your input, you'll get the logits. And this is exactly what we want out of the GPT model. So you get the logits in return, and this was the final GPT model. So let's see if our constructed GPT model outputs the correct dimensions. So I'll take two sentences. I'll append both the sentences in a batch, and my shape is going to be 2, 4. Then all I need to do is I need to pass this batch to my GPT model and check my outputs. So this is my output, and my output shape is 2 cross 4 cross 50,257, which is exactly what I want, because I have two batches of 4 tokens each, and each token has 50,257 probabilities, which I will be comparing it to the one hot target vector, and I'll be getting my loss. So we have successfully implemented the GPT architecture and produced an output of the correct shape from it. So if you want to explore more, you can definitely build on top of this and learn all these concepts. So for those of you who have been following this far, thank you for watching this video, and I will see you in the next one.